Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered if there is a more scientific way to figure out if one treatment works better than another, especially when you want to switch between them really fast? Well, today we are diving into a fascinating study that explores just that using a fancy statistical tool called Generalized Linear Mixed Models for alternating treatment designs. So what is an alternating treatment design, or ATD? You ask researchers use these designs when they want to compare different interventions quickly. Imagine you are trying to help someone with a behavior. Instead of sticking with one treatment for a long time, an ATD rapidly switches between treatments to see which one is actually doing the trick. This is super useful for behaviors that change easily, and when you want to get a clear answer without a lot of waiting. The paper says these designs are great for evaluating readily reversible behaviors. This means behaviors that can change back and forth quickly. Now let's talk about how scientists analyze the data from these ATDs. When we are dealing with things like counting behaviors or how often something happens, the data is often not like a smooth straight line. It can be a bit messy and have more variation than expected. Traditional methods might not be the best fit. That is where generalized linear mixed models, or GLMs, come in. Think of GLMs as a super sophisticated way to look at data that is counted or is in proportions. It can handle complex patterns and account for the fact that we are looking at the same individuals multiple times. The researchers in this paper want to see how well GLMs work specifically for ATDs which have this rapid switching of treatments. They are looking at count data, which is common in these studies, like counting how many times a student answers a question correctly, or how many challenging behaviors occur. To really test how well these ELMs work, the researchers did something cool. They ran a giant computer simulation. This is like a stress test for their statistical method. They created thousands of fake datasets that mimicked real AT data. They tweaked different things like how many people were in the study, how long the study lasted, and how big the treatment effects were. This helps them understand when and how the GLMs perform best. One of the key things they looked at in their simulation was bias. Bias is basically a systematic error in an estimate. If a method is biased, it consistently overestimates or underestimates the true effect. The good news is that for the most part, the GLMs they tested showed very little bias. This is a great sign. The paper states that the average bias for the immediate effect was small and close to zero across different model specifications. This means the estimates from the models were pretty accurate. Another important measure of performance is mean squared error, or MSE. MSE tells us how close the model's predictions are to the actual data. A lower MSE means a more precise and reliable estimate. In their simulation studies, they found that the average MSE for both the immediate effect and the trend change was small. This suggests that the GLMs used in their study are efficient at capturing the effects of the treatments. The paper mentions that the number of cases had a dominant influence on the MSE for the immediate effect, meaning more participants generally led to more precise estimates. Now, coverage rate is a bit trickier to explain. It is essentially how often the statistical confidence intervals produced by the model contain the true effect. If a model has good coverage, it means that about 95% of the time its confidence interval will actually include the real treatment effect. This is crucial for making reliable conclusions. They found some differences here depending on the specific GLM model and software used. Models that accounted for overdispersion and used small sample corrections tended to have coverage rates closer to the desired level. Specifically, the GLMMs procedure with Kenward-Roger correction performed well. The type-I error rate is something we all want to keep low. It is the chance of concluding there is an effect when in reality there isn't, basically a false positive. The researchers found that some models, especially those fitted in R without accounting for potential overdispersion, had inflated type-I error rates. However, when they used negative binomial models and the GLMMs procedure, the type-I error rates were well controlled and within an acceptable range. This is super important because inflated type-I errors can lead to believing a treatment works when it actually doesn't. They also looked at model fit using ASE and Beak. These are like scores that tell us how well a model fits the data while also penalizing for complexity. In their simulations, the negative binomial models generally had better fit scores than the Poisson models, indicating they were a better choice for the count data they were working with, often meaning the data had more variability than a simple Poisson model could handle. So what does all this mean? The main takeaway from this study is that GLMs are a powerful and reliable tool for analyzing count data in alternating treatment designs. When used correctly, especially with methods that account for overdispersion and potential small sample sizes, like the ones they tested with GLMMs, GLMs can provide accurate estimates and trustworthy statistical inferences for both immediate treatment effects and changes in trends of outcomes over time. The study highlights that understanding both the immediate impact and the long Term trend is vital for fully grasping a treatment's effectiveness. Now, no study is perfect, and the researchers are upfront about the limitations. Their findings are based on specific types of ATDs and count data. They mention that ATDs with proportional outcomes or different designs like adapted alternating treatments designs might need further investigation. They also point out that though their GLM framework is robust in the future work, could explore modeling even more complex variations like heterogeneity across cases. Or more adaptive designs, the researchers also emphasize the importance of design-comparable effect sizes. They introduced the concept of within-case incidence rate ratio, or WC. IR as a way to quantify effects that can be compared across different single-case studies. They also discuss the need for future work to develop between case incidence rate ratios for ATDs, so findings can be more easily synthesized in meta-analyses. This is crucial for building a strong evidence base for effective interventions. So to sum it up, this research gives us a really solid statistical foundation for analyzing data from alternating treatment designs, especially when dealing with count data. It tells us that we can trust GLMs to give us accurate answers about treatment effectiveness, as long as we choose the right model and use proper statistical corrections. This is fantastic news for researchers and ultimately for the individuals who benefit from these interventions. The real-world implications are huge because better analysis leads to better understanding of what works, which in turn leads to better practice. It's all about translating complex data into actionable insights. What do you guys think about using these advanced statistical models for single case designs? Let me know in the comments below. If you found this breakdown helpful, please give this video a thumbs up and subscribe to RUBIN'S Mind Lab for more explorations into the fascinating world of psychology research. Until next time, keep asking questions and stay curious.